All right, so we're continuing our foray into looking at all the different d electron configurations and spin states for five-coordinate transition metal complexes, trigonal bipyramidal versus square pyramidal. We left off. Last one we did was D4, so we're on D5. D5, we have several different spin states allowed. Let's start out with the doublet. Doublet, one unpaired electron, S equals 1/2. If you compare the TBP versus the SP, TBP has this 9/8 E sigma term. The SP doesn't. So TBP is going to be way more, is going to be way less stable, right? It's going to be destabilized compared to SP, which is much lower in energy. So it's always going to be SP no matter what your ligands are. What if we go to S equals 3/2 state? This would be a quartet where we have three unpaired electrons. And this gets close, right? Why? Well, you have 13 e pi here, and here you have what's 27 halves. That's 13 and a half e pi. So that's pretty much a wash. Maybe a strong pi donated ligand would prefer SP from that standpoint, but pretty much a wash because e pi is so little, right? And then you have 2 e sigma versus 2.25 e sigma. So you're only a quarter e sigma off. So that doesn't matter much. So e sigma is pretty much a wash. So if you have bulky ligands, that means probably you're going to be back to the VSEPR geometry, TDP. If you have strongly pi donating ligands, especially if they're small, okay, that's probably going to mean SP, right? D5, this is a sextet, right? 2s plus 1, so 2 times 5/2, plus 1 is 6, so we call it a sextet. That's 5 unpaired electrons. That's going to be 5 e sigma plus 10 e pi for both TBP and SP. This makes sense. This is a half-filled electron configuration, right, where all the orbitals are half-filled, so they're equal because the barycenter of all these, the center lines of all these is the same. All we're doing is changing the geometry, so we're just changing the splitting, right? So it makes sense that they should be the same. And because they're the same, that means you're going to prefer trigonal bipyramidal due to steric reasons. We default back to the VSEPR geometry. And indeed, this iron chloride complex, which is D5 and pentet, is a sextet, sorry, is TBP. One thing I should note at this point is, for octahedral and tetrahedral complexes, we spent a lot of time talking about high spin and low spin, right? This is high spin, 5/2, F equals 5/2. This is probably called medium spin, but nobody says that. And this is called low spin, right? So nobody uses the terms low spin, medium spin, or high spin when you're talking about these other geometries. You just give them what the spin is. For octahedral and tetrahedral, it's so commonplace to talk about high spin and low spin because these are very common coordination geometries. And there's only two possibilities there because the 5D orbitals are only split into two energy levels. But here we're split into 3 energy levels or even 4 energy levels here. So there's a lot of different possibilities, okay, which makes the chemistry quite rich, right? All right, so we're done with D5. Now let's do S0. S0, this is a singlet for D6. S0, TBP is actually not possible. And if you try to make a singlet for this, let's just try. What would happen? So a singlet means we have to pair our electrons. Well, we want to pair them as much as possible. So we go like this, and then we go like that. But we can't do that because that's violating Hund's rule. This is an excited state now. It's not a ground state. So we have to put these in separate orbitals. And when we do that, now we're no longer a singlet, we're a triplet. Okay, so that can't happen. That's an excited state. So this one, of course, is going to be SP. And indeed, there are certain singlet G6 complexes that use some sort of macrocycle, and those are stable square pyramidal complexes. What about S1 D6, where now we're okay having a triplet? 9/4 E sigma versus 2 E sigma. We've seen that before. Those are in 0.25 E sigma away. That's awfully close. 17 E pi versus 16 E pi. That's going to be one of these cases, again, where if you have very sterically demanding ligands because your E sigmas are very close, only 1/4 E sigma away, that's going to tell you that sterically demanding ligands are going to prefer the sterically more free geometry, the VSEPR geometry that has more space where the ligands are far apart from another, which is TVP. But if you have small ligands, especially if they're strongly pi donating, right, where that E pi factor could make a difference, then you're going to be SP. What if you have a pentet? This is 4 unpaired electrons. Pentet 2s plus 1, 2 times 2 plus 1 is 5. D6 configuration. Here, 5 E sigmas wash out, and you're only a half a E pi away. So this is going to be back to one of these D1, D2 type cases where probably you're going to be TBP, but if you have a strongly pi donating ligand, you might be SP. D7 doublet. D7 doublet is looking like 20 E pi versus, what is that, 18 and a half E pi. So there's a little bit of a difference here. And this is 3.75, 3 and 3/8, okay. 3 and 3/8 versus 2 E sigma. So we're 1 and 3/8 E sigma difference. That's a lot of difference. So definitely this is going to destabilize the structure, having all that E sigma. So we're definitely for D7 doublet going to be square pyramidal. Okay. What about D7 for this spin state with S equals 3/2? Look at these. You're at 5 E sigma versus 5 E sigma. You're only 1 E pi difference. So this gets back to the old D1, D2 cases where you're going to be TBP unless you have a strongly pi donating ligand, in which case you might be SP. All right, what about, oh, here's an example where this nickel complex is D7 has the spin state and is a quartet, right, and is going to be TBP, the steric geometry. All right, what about D8 singlet? We're almost there, guys, done all these. This one is going to be dependent on the ligand size. We have a 20 E pi and a 20 pi, that's a wash. And we have a 3/2 E sigma and, 4/2 E sigma and a 4 E sigma. So there is a slight preference for square pyramidal, definitely, half a E sigma. But if you have really bulky ligands, you might be TBP because half E sigma isn't that much. Triplet D8. We are definitely going to be square pyramidal here because we have 5 E sigma for square pyramidal, and we have 6 and 1/8 E sigma. So it's more than one E. It's more than 1 E sigma higher for the TBP. So we're definitely going to be square pyramidal. D9. D9 is going to be a close call here. 20 E pi versus 20 pi is washed. And we have 7 E sigma versus 29/4 E sigma. And so that is what, 6 and 3. That's fairly, it's fairly close. Okay, so it's what, 7 and 1/4 E sigma. So that's only 1/4 E sigma. So that's basically very little. So if you have very bulky ligands, you're definitely going to be TBP. Whether or not it's pi donating or pi accepting doesn't matter because the E pi parts are equal, right? But if you have big ligands, it's going to be TBP. Otherwise, you'll have a slight preference for square pyramidal. And you can see that here. This copper bromide complex is TBP. Only has 1 atom ligands. But when you have an ammonia complex, which has larger ligands, because ammonia has 4 atoms in it, then you're actually square pyramidal. So that's kind of cool, borne out by experiment. D10, you're have a full hand of electrons, so they're all going to be equal. 10 E sigma plus 20 E sigma, who cares? They're all equal, so you're back kind of to the VSEPR basics, so TBP due to sterics. And that's true if you look at a D10 complex that is 5 coordinate, like the zinc complex. This is a zinc and it's 2 plus 8. Zinc is in the 12th 12th column, excuse me, of the periodic table. So that's a D10 metal, and it is indeed following VSEPR. All right, so I know that was a lot there. We're kind of done with this section now about angular overlap method, but we'll be doing some practice problems in the homework, and certainly we can discuss this more during our scheduled class time. But I think it's very powerful how much information you can get. We went through this relatively quickly, right? Going through all these different electron configurations, spin states, and we're able to make predictions that are in line with experiments that aren't using any a priori assumptions that are based on quantum mechanics. And so it's really, really, really a powerful theory. So I hope that you guys are at least able to appreciate that a little bit.